review. Let's see if I can draw on this. Here we go. Kinetic theory. You're going to be asked about gases as compared to liquids. Now look at this. Both flow. All right, so that's not a difference. But there is a big, big difference between liquids and gases. You see, liquids, there is an attraction between the particles, okay? Whereas gases, the particles are far apart, they're independent, they're colliding with the walls of the container, or they're colliding with objects, and that's causing gas pressure. Because of the space between the particles, gases are compressibles. The particles are close in a liquid, so you can't really compress a liquid. The volume of a liquid remains constant, whereas the volume of a gas can change. What kind of collisions are all these particles experiencing? Perfectly elastic collisions, meaning there's no loss of energy. Atmospheric pressure. Let's review. This is a barometer, and it measures atmospheric pressure. Okay, these are the conversion factors. You'll need to bring your calculator. These are the ones you need to know. kPa, atmospheres, and millimeters of mercury. So let's do a couple conversions. Let's start with less than 760. Let's say 500 millimeters of mercury. Let's convert that to atmospheres. How many atmospheres is that? Well, let's see. You set up your labels. If you want to get rid of millimeters of mercury, it has to go on the denominator. And if you want to end up with a label of atmospheres, then that label goes in the numerator. What numbers go with what? One atmosphere. I only go to one ATM machine at a time. And 760 millimeters of mercury. Okay? Then you divide and you will get atmospheres. How about another one? 700 millimeters of mercury. This time we're going to convert it to kPa. So if we want to end up with the kPa's, we put the label there. And if we want to get rid of millimeters of mercury, we put that label there. Now, once you have your labels done, you put in your numbers. 101.3, it almost sounds like a radio station, doesn't it? 760 millimeters of mercury. You use your calculator, you multiply the numerator, divide it by the denominator, and you end up with kPa. Next slide, I want to talk about pressure changes as you go change in elevation. Now the first thing I want to point out is sea level. Sea level is right here. Notice the number 101.3 kPa. At sea level, we have water boiling at 100 degrees Celsius. That is the normal boiling point of water at normal pressure, 101.3 kPa. All right. As you go up in elevation, the pressure, the atmospheric pressure, decreases. And so you are able to boil at less than 100 degrees Celsius. Now let's take a look at going below sea level. Here we go. Below sea level, you will have more pressure. You will experience more pressure. So below sea level is where water might boil at 105 degrees Celsius. Above sea level, it will boil less than 100 degrees Celsius, like 98 degrees Celsius. Even at Everest, it boils at about 70, I'm going to go with 78 degrees Celsius. I forget the exact number. Okay? Next, I want to look at evaporation of a liquid. So you see, these are the liquid particles. They're moving, kinetic theory. This is a closed system, and this is an open system. So the particles, the surface particles with the most kinetic energy will be the ones that evaporate first, leaving behind the lower kinetic energy particles. Now, these particles absorb energy from the surroundings, so a higher temperature speeds up the rate of evaporation. A lower temperature slows it down. A closed container these particles are gas particles because they've evaporated. That means above the liquid, vapor pressure will build up. Okay, so once you put a lid on the container, you will build up vapor pressure, and then you will reach what's called dynamic equilibrium, where the rate of evaporation is equal to the rate of condensation. Again, evaporation is a cooling process. And now we're at our last slide. Let's compare these two liquids. These are water molecules. And let's see. Let's say that this container of water is at 20 degrees Celsius, and let's say this one is at 40 degrees Celsius. Okay, and let's put a lid on this container. Here we go, a lid. Just going to draw it like that. Okay, and so one of these has more vapor. This one. So it has more vapor pressure above the liquid. Again, temperature changes. Two different liquids, two different temperatures. The one at the lower temperature, that slows down the rate of evaporation. The one at higher temperatures increases the rate of evaporation. This one has more vapor pressure. This one has less vapor pressure. Okay, get some good sleep, and I believe I covered all 15 items that will be on the quiz. Good night.